As many of you know, I am a math nerd. And as a math nerd, I really like playing with shapes. Right now, for example, I'm playing with triangles. Of course, the triangle I'm playing with right now is not the triangle in my hand. This is a triangle in my imagination. It's not made up of jiggly little molecules. Instead, perfect, smooth lines. These lines are, of course, one-dimensional, not the lines with the width on my paper. In fact, my entire imaginary triangle is two-dimensional, not a 3D piece of paper. But still, there's so many triangles I can make. There's nice equal triangles, and long pointy triangles, and short flat triangles, and little tiny triangles, and big triangles that take up the full page, and triangles, and triangles, and triangles. And now I'm getting curious, as mathematicians often are. When I draw this triangle, I still have so many choices on what triangle I'm going to make. I can still make this line into a big pointy triangle or a short flat triangle. But at what point have I decided that this is the sort of triangle that I'm going to make? I can start trying different options. If I start by drawing the endpoints, then I have these 3 planes right here, then I know exactly which triangle I'm going to make. I have to make this triangle that connects these planes. I cannot make any other triangle but this one triangle right here. But what if I make a triangle out of wood or out of popsicle sticks? I have these popsicle sticks at the length I want them to be. Now there's only one way I can stick them together at the ends that will form a triangle. So by cutting the sides at this specific length, I've decided what triangle it's going to be. But what if I only have 2 sides? Then I can spread them far apart to make a long flat triangle. Or I can push them close together to make a short, thin, and tall triangle. Or I can do anything in between. But once I decide how far apart they are, this angle over here, then I know exactly which triangle it must be. Actually, speaking of angles, what if we only have angles? No sides at all. Have we decided what triangle we're making? Or do we still have so many options? Here, I made these angle sleeves so I can see what happens when I know the angles but not the side lengths. I can push these close together, and I can slide these around on these sides to change the length. So I don't know exactly what triangle it is. I can slide these around, I can move it apart. There's so many triangles I can still make. But it's only getting bigger or smaller. But it's still the same sort of triangle. It's not changing its shape at all, it's just a bigger version or a smaller version. Now we've found out something. And when mathematicians find out something, they like to make a function for it. Think of a function as a magical black box, or just a computer. You stick in an input, and it spits out an output. We want the input to be the angles, and the output to be the shape of the triangle. Since we're being mathematicians, we need to describe the shape in numbers. We can describe the shape in the ratio of the sides. See, no matter how big or small this one shape is, the amount of times that this side is going to fit into this side is always going to be the same. The problem now is that the input is too vague. We have to input 2 different angles in this function in order to make it work, since we don't know what triangle it is until we have 2 of the angles. So to make things simpler, we'll only work with the right triangles, which is triangles with one side being 90 degrees. I have this right triangle here, and I want to say that I'll say this angle right here. I'll call it apple, because apples are cool. So this angle right here, if you have a right triangle and it has this angle, apple, then the triangle is going to be sort of short and long, like this. Now we said that the output of the function is going to be the ratio of the sides. But mathematicians have actually defined 3 different functions, depending on which ratio you're trying to find. So the sine of apple is the opposite side, the side across here, over the hypotenuse, the longest side of the right triangle, the side across from the right angle, which is 3 over 5 in this case. The cosine of apple is the adjacent, the side touching the angle, not the hypotenuse, the other side touching the angle, and over the hypotenuse, which in this case would be the 4 here divided by the 5, or 4/5. Then the tangent would be the opposite side over here over the adjacent side over here. In this case, this would be 3 over 4. I like to remember this by the acronym SOHCAHTOA, which I learned on Khan Academy. Here we can see that you have sine opposite hypotenuse. The sine of apple is the opposite side over the hypotenuse. Then you have ka. Ka stands for cosine adjacent hypotenuse. The cosine here, the cosine of apple, is the adjacent side, the side next to apple, over the hypotenuse. And finally the tangent, toa. Tangent opposite adjacent. The tangent side is the opposite side over the adjacent side. For all the work we're going to be doing playing around with these functions in the future, it's important that we know what each of them means. It's also important to note that right now, our functions only work for angles that fit into a right triangle. They have to be able to work in a right triangle, since our function only works for this angle in a right triangle. So if it's bigger than 90 degrees, it's obviously going to be too large to fit into a right triangle. So those angles don't, so you can't plug those angles into these functions right now. And you also can't have an angle that's 0 degrees or an angle that's negative, because those are too small to fit into a right triangle. I'll let you try it out for 90 degrees and see what happens when you do that. We'll expand this function to all angles in the next video, but for now, that's it. See you next time.